Good morning, everyone. My name is Debojyoti Vishwas. I am an assistant professor at Shiv Nadar University, Chennai. I gave a brief talk on the glimpses of quantum computing and machine learning at a recently conducted FDP, and I wanted to share my talk with everyone. So I'm just sharing it here. Hope you will find it interesting. So, quantum computer is a computer that exploits quantum mechanical phenomena. On small scales, physical matter exhibits the properties of both particles and waves, and quantum computing leverages this behavior using specialized hardware. Classical physics cannot explain the operation of these quantum devices, and a scalable quantum computer could perform some calculations exponentially faster than any modern classical computer. Theoretically, a large-scale quantum computer could break some widely used encryption schemes and aid the physicists in performing physical simulations. However, the current state of the art is largely experimental. The basic unit of information in quantum computing, the qubit or quantum bit, serves the same function as the bit in classical computing. However, unlike a classical bit, which can be in one of the two states, 0 or 1, a binary, a qubit can exist in a superposition of two basis states, which loosely means that it is in both states simultaneously. When measuring a qubit, the result is a probabilistic output of a classical bit. Also, in principle, a classical computer can solve the same computational problems as a quantum computer, given enough time. Quantum advantage comes in the form of time complexity rather than computability, and quantum complexity theory shows that some quantum algorithms are exponentially more efficient than the best known classical algorithms. A large-scale quantum computer could, in theory, solve computational problems unsolvable by a classical computer in any reasonable amount of time. The concept of extra ability has been called quantum supremacy. While such claims have drawn significant attention to the discipline, near-term practical use cases still remain a little limited. Uh, I have a video here. This video explains the phenomena of a quantum superposition. Imagine touching the surface of a pond at two different points at the same time. Waves would spread outward from each point, eventually overlapping to form a more complex pattern. This is a superposition of waves. Similarly, in quantum science, objects such as electrons and photons have wave-like properties that can combine and become what is called superposed. While waves on the surface of a pond are formed by the movement of water, quantum waves are mathematical. They are expressed as equations that describe the probabilities of an object existing in a given state or having a particular property. The equations might provide information on the probability of an electron moving at a specific speed or residing in a certain location. When an electron is in superposition, its different states can be thought of as separate outcomes, each with a particular probability of being observed. An electron might be said to be in a superposition of two different velocities or in two places at once. Understanding the superposition may help to advance quantum theory and technology such as quantum computers. I want you to go through this video. This is from Wikipedia superposition article. Okay, so we don't want to infringe any copyright. This is just for educational purposes. Thank you. So conceptually, Schrodinger's equation is the starting point of the superposition phenomena. Schrodinger's equation is the quantum counterpart of Newton's second law in classical mechanics. Given a set of known initial conditions, Newton's second law makes a mathematical prediction as to what path a given physical system will take over time. The Schrodinger's equation gives the evolution over time of the wave function, the quantum mechanical characterization of an isolated physical system. This equation was postulated by Schrodinger based on the postulate of Louis de Broglie that all matter has an associated matter wave. Quantum superposition is a fundamental principle of quantum mechanics that states that the linear combination of solutions to the Schrodinger equation are also solutions of the Schrodinger equation. Let me recap this again. It states that the linear combination of solutions to the Schrodinger equation are also solutions of the Schrodinger equation. This follows from the fact that the Schrodinger equation is a linear differential equation in time and position. In quantum physics, a quantum state is a mathematical entity that embodies the knowledge of a quantum system. Quantum mechanics specifies the construction, evolution, and measurement of a quantum state. The result is a prediction for the system represented by the state, knowledge of the quantum state, and the rules for the system's evolution in time exhausts all that can be known about a quantum system. The other phenomenon which we generally note in this area are quantum entanglement. This is the phenomenon of a group of particles being generated, interacting, or sharing special proximity in such a way that the quantum state of each particle of the group cannot be described independently of the state of the others, including when the particles are separated by a large distance. The topic of quantum entanglement is at the heart of the disparity between classical physics and quantum physics. Entanglement is a primary feature of the quantum mechanics which is not present in classical domain. Measurements of physical properties such as position, momentum, spin, and polarization performed on entangled particles can in some cases be found to be perfectly correlated. For example, if a pair of entangled particles is generated such that their total spin is known to be zero and one particle is found to have clockwise spin on a first axis, then the spin of the other particle measured on the same axis is found to be anticlockwise. However, this behavior gives rise to seemingly paradoxical effects. Any measurement of a particle's properties result in an apparent and irreversible wave function collapse of that particle and changes the original quantum state. With entangled particles, such measurements affect the entangled system as a whole. In quantum mechanics, the wave function collapse, also known as the reduction of the state vector, occurs when a wave function, initially in a superposition of several eigenstates, reduces to a single eigenstate due to interaction with the external world. This interaction is called an observation and is the essence of a measurement in quantum mechanics, which connects the wave function with classical observables such as position and momentum. Collapse is one of the two processes by which quantum systems evolve in time. The other is the continuous evolution governed by the Schrodinger equation. Such phenomena were the subject of a 1935 paper by Albert Einstein, Boris Podolsky, and Nathan Rosen, and several papers by Erwin Schrödinger shortly thereafter. This described what came to be known as the EPR, Einstein-Podolsky-Rosen paradox. Einstein and others considered such behavior impossible, Einstein referring to it as spooky action at a distance, and argued that the accepted formulation of quantum mechanics must therefore be incomplete. Later, however, the counterintuitive predictions of quantum mechanics are verified. Quantum computing extensively uses bracket notation. A ket is of the form you can see here, one bar and then one arrow. Inside that there is a vector v. Mathematically denotes a vector v in an abstract or complex vector space, capital V, and physically it represents a state of some quantum system. A bra is of the form in the left hand side arrow, then if, then the vector, then one vertical bar. Mathematically it denotes a linear form, that is a linear map from mapping each vector in capital V set to a number in the complex plane C. Letting the linear function act on a vector bra if act on a vector ket V is written as bracket if V, which is an element here bracket if V, which is an element of the complex plane C. A binary digit characterized as 0 or 1 is used to represent information in classical computers. When averaged over both of its states 0 and 1, a binary digit can represent up to 1 bit of information, where a bit is the basic unit of information. However, in this article, the word bit in presentation also, it's synonymous with the binary digit. In classical computer technologies, a processed bit is implemented by one of the two levels of low direct current voltage. And whilst switching from one of these two levels to the other, a so-called forbidden zone between the two logic levels must be passed as fast as possible, like from 0 to 1, as electrical voltage cannot change from one level to another instantly. There are two possible outcomes for the measurement of a qubit, usually taken to have the value 0 and 1, like a bit. However, whereas the state of a bit can only be binary, either 0 or 1, the general state of a qubit, according to quantum mechanics, can arbitrarily be a coherent superposition of all computable states simultaneously. Moreover, whereas a measurement of classical bit would not disturb its state, a measurement of a qubit would destroy its coherence and irrevocably disturb the superposition state. In quantum mechanics, the general quantum state of a qubit can be represented by a linear superposition of its two orthonormal basis states or basis vectors. These vectors are generally denoted as ket0 equals to 1 0 matrix and ket1 equals to 0 1. They are written in the conventional Dirac notation or bracket notation. These two orthonormal basis states, ket0 and ket1, are together called the computational basis. A pure qubit state is a coherent superposition of the basis states. This means that a single qubit psi can be described by a linear combination. Here alpha and beta are the probability amplitudes and they are both complex numbers. The probability of outcome ket0 with value 0 is norm of alpha square, and the probability of outcome ket1 with value 1 is norm of beta square. The identity gate is the identity matrix, usually written as I, and is defined for a single qubit as I equals to 1001, where I is the basis independent and does not modify the quantum state. There are many different gates and logic circuits like this, such as Hadamard gate, Toffoli gate, etc. They are discussions for a much longer course. And now coming to the algorithms, we have we will discuss 2-3 classical algorithms, and then we will discuss about their quantum counterpart. The k-nearest neighbor algorithm is a non-parametric supervised learning method. It was first developed by Evelyn Fix and Joseph Hodges in 1951. Most often it is used for classification as a KNN classifier, the output of which is a class membership. An object is classified by a plurality vote of its neighbors, with the object being assigned to the class most common among its k nearest neighbors. K is a positive integer, typically small, and if k equals to 1, then the object is simply assigned to the class of that single nearest neighbor. KNN algorithm can also be generalized for regression. The KNN regression, also known as the nearest neighbor smoothing. Here the output is the property value for the object. This value is the average of the values of k nearest neighbors. If k equals to 1, the output is simply assigned to the value of that single nearest neighbor, also known as nearest neighbor interpolation. The key steps of QKNN are also similar to this. In QKNN, the data points are encoded into quantum states. Each classical data vector is represented as a normalized quantum state in a high-dimensional Hilbert space. Hilbert spaces, named after David Hilbert, allows the methods of linear algebra and calculus to be generalized from finite dimensional Euclidean vector spaces to spaces that may be infinite dimension. A critical step in KNN is computing distances between the query point and data points. In QKNN, the distances are evaluated using quantum techniques such as the inner product or quantum amplitude estimation. A critical step in KNN is computing distances between the query point and data point. In QKNN, the distances are evaluated using quantum techniques such as the inner product or quantum amplitude estimation. For example, here distance varies with norm of ket x minus ket q whole square, where ket q represents the query point and norm x is represented with the two vertical bars. A norm is a function from a real or complex vector space to the non-negative real numbers that behaves in certain way like the distance from the origin. The next step is quantum search for nearest neighbors. Grover's algorithm or its variants can be used to search for the k nearest neighbors efficiently. By encoding the distances as quantum amplitude, Grover's search helps identify the smallest distances with fewer computational steps compared to the classical methods. The next step is level aggregation. After identifying the k nearest neighbor, their levels are retrieved and a majority vote or weighted average is performed. Depending upon whether the problem is classification or regression, this step may involve quantum measurement or classical post-processing. Grover's algorithm is a quantum algorithm that solves the unstructured search problem. In an unstructured search problem, we are given a set of n number of elements and we want to find a single marked element. A classical computer would need to search through all n number of elements in order to find the marked element, which would take a time of order n. Grover's algorithm, on the other hand, can find the marked element in the time of order of square root of n. Grover's algorithm is a powerful tool that can be used to solve a variety of problems. For example, it can be used to find patterns in data, break cryptographic keys, and solve optimization problems. As quantum computers become more powerful, Grover's algo will become increasingly important. The algorithm works by applying a series of quantum operations to the input state, which is initialized as a superposition of all possible search states. The key idea behind Grover's algo is to amplify the amplitude of the marked state, that is, the state containing the items that we are searching for, by iteratively applying a quantum operation known as the Grover operator. Here, first we discuss the advantages of QKNN. Number one, speed up. QKNN offers potential quadratic speedup in distance calculations and neighbor search using quantum techniques such as amplitude estimation and Grover's search. High dimensional data, quantum computers can natively handle high dimensional data, making QKNN particularly effective for problems with large feature spaces. Efficient storage, quantum states can encode exponentially large data sets in a compact manner using quantum superposition. Obviously, there are some challenges. This include number one, data loading. Encoding the classical data into quantum states is a non-trivial task and may offset some speed advantages. Errors and noise. Current quantum hardware is prone to errors and noise, which may impact the accuracy of distance computations and neighbor identification. Number three, interpretability. Quantum operations can be hard to interpret and debug compared to classical algorithms. Lastly, the applications include quantum enhanced pattern recognition, high dimensional data classification in quantum chemistry and finance, hybrid quantum classical systems for machine learning tasks. The QKNN algorithm represents a promising area of research in quantum machine learning with potential to outperform classical KNN under certain conditions as quantum hardware continues to improve. Now, classifying data is a common task in machine learning. Here we see another different algorithm called support vector machine or SVM. Suppose some given data points each belong to one of the two classes and the goal is to decide which class a new data point will be in. In the case of support vector machines, a data point is viewed as a p-dimensional vector, a list of p numbers, and we want to know whether we can separate such points with a p-1 dimensional hyperplane. This is called a linear classifier. There are many hyperplanes that might classify the data. One reasonable choice as the best hyperplane is the one that represents the largest separation or margin between the two classes. So we choose the hyperplane such that the distance from it to the nearest data point on each side is maximized. A hyperplane is a generalization of two-dimensional plane in 3D space. A support vector machine constructs a hyperplane or set of hyperplanes in a high dimension or infinite dimensional space. which can be used for classification, regression, or other tasks like outlier detection. Intuitively, a good separation is achieved by the hyperplane that has the largest distance to the nearest training data point of any class, that is so-called function margin. Since in general the larger the margin, the lower the generalization error of the classifier. A lower generalization error means that the implemented algorithm is less likely to experience overfitting. In the picture here, H1 does not separate the classes. H2 does, but with a small margin. H3 separates them with the maximal margin. Quantum support vector machines are a quantum extension of classical support vector machines, which are supervised machine learning algorithms used for classification and regression tasks. QSVMs leverage the quantum computing techniques to potentially improve the performance of SVMs, particularly in high dimensional feature space or large datasets. SVMs aim to find a hyperplane in a high dimensional space that best separates data into different classes. The support vectors are the data points closest to the hyperplane, which determine its position and orientation. Also, SVMs often use kernels to project data into a higher dimensional feature space where it becomes linearly separable. QSVMs replace the classical kernel with a quantum kernel computed using quantum computers. A kernel function measures the similarity between the two data points, and quantum computers can compute the complex similarity measures efficiently in certain cases. Quantum states encode data, and the kernel captures the overlap or similarity between these states. Quantum computers can potentially compute kernel function faster than classical methods, especially for higher dimensional data. Grover's search and other quantum algorithms may speed up the optimization steps during training. QSVMs often adopt a hybrid quantum classical approach. Here are two steps. Number one, quantum step, where we compute the kernel matrix using a quantum computer, and classical step, when we use the classic kernel matrix in a classical SVM optimization algo to find the hyperplane and classify data. There are many challenges of QSVM, which include typically four issues. Number one, quantum state preparation, where we have to encode the classical data into quantum states, which is resource intensive and might offset the speed gains. Number two, noise and errors. Current quantum hardware is prone to noise, which can affect the accuracy of the kernel computations. Interpretability. The quantum feature space is less interpretable than the classical kernels, making it harder to understand why certain decisions are made. Number four, scalability. For very large dataset, the cost of kernel matrix computation and the state preparation might become prohibitive. Applications of QSVM include quantum chemistry and material science for classifying molecular properties and the phase of materials. In finance, the portfolio optimization and the fraud detection, and in healthcare, classification tasks like disease prediction based on genetic data or medical data. Quantum neural networks are the third model which we will look into. They are a class of machine learning models that blend concepts from quantum computing and artificial neural networks. They aim to leverage the principles of quantum mechanics, such as superposition and entanglement, to achieve the advantages over classical neural networks, particularly in speed, scalability, and learning capacity. Classical data is encoded into quantum states, often using techniques like amplitude encoding or basis encoding. Quantum gates and circuits are used to build the layers of QNN. These layers operate on qubits and can introduce entanglement and interference, mimicking the nonlinear transformations in classical neural network. Most QNN implementations use a hybrid approach. One is quantum part. Quantum circuit performs computation that represent the forward pass of a neural network. And then there is the classical part, which has the classical optimization algorithms like gradient descent used to update the parameters, often by measuring quantum observables. The other term which we come across here is the variational quantum circuit or VQC. There are common framework for QNNs where a parameterized quantum circuit is trained to minimize a loss function. Parameters, and which are the angles of quantum gates, are updated iteratively using classical optimization. The advantage of QNN can be their expressive power. QNNs can encode and process the information in exceptionally large Hilbert spaces, enabling them to represent the complex functions efficiently. Next, their speedup. For certain problems, QNNs can achieve computational speedups, especially in tasks like pattern recognition or optimization. Third, entanglement and superposition. These quantum features allow the QNNs to explore multiple states simultaneously, potentially leading to better learning outcomes. Lastly, resource efficiency. Quantum devices can simulate high-dimensional neural network architecture without requiring an exponentially large number of parameters. So in this slide, with this we will end. Here we represent some of the quantum computing events that are happening in Indian scenario. So India is actively building a quantum ecosystem powered by government support, academic research, and private sector collaboration. This ecosystem encourages the strategic alliance between government, industry, and academia, supporting advancements in fields ranging from quantum computing, communication, and cryptography to sensing and material science. So at the heart of India's quantum ambition is the National Quantum Mission (NQM), approved by the Union Cabinet on 19th April 2023, with a budget allocation of approximately 6,000 crore for the period of 2023 to 2031. This mission complements the India's commitment to advancing quantum technologies. So there are many challenges that Indian academia and industry face for quantum computing till now. Challenges are in three parts: talent, infrastructure, and limited innovation culture. Quantum computing is altogether a unique way of computation, though the learning curve is quite high and needs talent which has a mix of scientific and technical skills. In last few years, the quantum infrastructure has matured significantly and is evolving rapidly. Okay, getting proper hardware and experimental setup, understanding the mathematics, and to train dedicated students, all of them are quite difficult tasks, and the Indian workers are are researching on it. There are a few companies working in this area in India. One is QNU, and IBM are some of them. And here in the slide, I have mentioned a few interesting papers and websites for entering in research in this area. Please let me know if you have any queries or email to me if any issue with the presentation. Thank you.